By introducing the concept of electric flux, we can elucidate the topological properties of electric field. The electric flux or the flux of an electric field is defined as the number of the electric field lines that intersects a given area. With other words, the flux is the rate of flow of the electric field through a surface per its area. If the electric field E is uniform, the electric flux phi E passing through a planar surface S perpendicular to the field lines is given by the magnitude E of the electric field, times the surface area S. If theta is the angle between the direction of the field lines and the normal n of the planar area S, then the electric flux phi E is equal to E times S times cosine theta, that is E times the area S perp projected into the direction of the field lines, or equivalently, the projection En of the electric field strength on the surface normal n, times the surface area S. By introducing the area vector for the surface S as the surface area S times the surface normal n, we can write the flux phi E as the scalar product of the electric field strength E and the area vector S. Let us consider a more general case where the electric field E is not uniform and the surface S has an arbitrary shape. We partition the surface S into the surface area elements delta Si, such that they are small enough to be approximated with planar area elements over which the electric field Ei can be considered constant. Then the electric flux phi E through the surface S can be approximated with the scalar product of Ei and delta Si from I equals to 1 to n. Here n is the number of the area elements covering the surface S. If we refine the partitioning of the surface S such that the area delta Si approaches 0 for each index I while the number of the area elements tends to infinity, we obtain a surface integral from the sum. That is, the electric flux phi E through a surface S is given by the integral of the electric field strength E over the surface S. In the case of closed surfaces we can apply the same method, and the electric flux phi E intersecting the closed surface S is also given by the surface integral of the electric field strength E over the closed surface. By convention, the area element vector ds on a closed surface is directed perpendicularly outwards, that is, its direction in a given point on the surface is given by the outward surface normal in that point. For the electric field lines piercing the closed surface S, the surface can be split into the part S1, where the field lines are directed out of the closed surface, and the part S2, where the field lines are directed into the closed surface. In the first case, the angle between the surface normal and the electric field strength E over the surface S is less than pi over 2. Therefore, the scalar product of these vectors is greater than 0, and the electric flux is positive over the surface S1. On the contrary, the angle between the surface normal and the electric field strength E is greater than pi over 2 over the surface S2, and the electric flux through the surface S2 is negative. As a result, if all the electric field lines entering into the volume enclosed by the surface exit the volume, then the total electric flux through the surface vanishes. With other words, if no electric field lines originate or terminate within the volume enclosed, the net electric flux through the closed surface S is 0. Now we can determine the flux through an arbitrary closed surface for the electric field due to a point charge. We calculate the electric flux when the point charge is inside and outside the volume enclosed by the surface. We start with the simplest case, where a positive point charge Q is placed at the center of a spherical surface S with the radius r. Then both the electric field strength E due to the point charge and the surface normal N are perpendicular to the sphere in its each point. As a result, the electric flux phi E through the sphere is equal to the magnitude E of the electric field measured at the surface, times the total area S of the sphere with the radius r. The first factor of the product is given by Coulomb's law, which states that the magnitude E of the electric field at the distance r from the point charge Q is equal to 1 over 4 pi times epsilon naught, times Q divided by r squared. The second factor, that is the surface area of the sphere, is given by 4 pi times r squared. As a result, we can write the flux as the charge Q over 4 pi times epsilon naught times r squared, times 4 pi times r squared. Then we obtain Q divided by epsilon naught. Since the flux through the closed surface S is the surface integral of the electric field strength over the surface, we can conclude that the surface integral of the electric field strength E of the point charge Q over the sphere S with the point charge in its center gives the charge Q divided by epsilon naught. If the point charge Q is inside a closed surface S of an arbitrary shape, we can calculate the flux element through an infinitesimal area element ds on the surface. The flux element d phi E is given by the dot product of the electric field E at the area element and the area element vector ds. The dot product can be written as the magnitude of the electric field at the area element, times the area ds times cosine theta, where theta is the angle between the direction of the electric field at the area element, and the normal n of the area element. If d omega is the solid angle subtended by the surface element ds, then the projection dsr of the surface element perpendicular to the electric field E also subtends the solid angle d omega at the distance r from the point charge. Here ds times cosine theta is the projected area element dsr. Then we can apply Coulomb's law, and write the flux d phi E as q over 4 pi times epsilon naught, times dsr over r squared. But the projected area element dsr is equal to the square of the distance r, times the solid angle d omega subtended by the area element. As a result, we obtain q over 4 pi times epsilon naught, times d omega. We have already seen that the integral of the electric field over the closed surface S is equal to the electric flux phi E through the surface, which is given by the integral of the contribution d phi E over the whole closed surface S. By substituting the result we derived above, we obtain q over 4 pi times epsilon naught times the integral with respect to the solid angle over the whole surface S. If the surface S is such that the lines originating from the point charge q intersect the surface only once, then the integral represents the solid angle subtended by the unit sphere, which is 4 pi. This gives q over epsilon 0, as in the case of the sphere. In the case of a surface where the lines originating from the point charge q intersect the surface more than once, we proceed as follows. For example, if the lines originating from the point charge intersect the surface 3 times, then the surface area elements subtending the solid angle d omega are ds1, ds2 and ds3. Since the electric field of the point charge is spherically symmetric, the magnitude of its flux is the same through all the 3 area elements. The only difference is that the flux is positive over the area elements ds1 and ds3, and negative over the area element ds2, which can be seen the angles between the directions of the area element vectors and the one of the electric field. As a result, the fluxes through the area elements ds2 and ds3 cancel out, and only the flux over the area element ds1 has a contribution to the net flux over the whole surface S. Whenever the number of the intersections is odd, we have the same result. Then the projections of the area elements providing a contribution to the net flux cover a whole sphere with the point charge in the center without overlapping each other, and the integral gives the solid angle subtended by the sphere again, which is 4 pi. Now we can conclude that if a point charge q is in the volume enclosed by an arbitrary surface S, then the integral of the electric field due to the charge over the surface S is equal to charge q divided by epsilon naught, as in the case of the sphere. After having determined the flux through a closed surface due to a point charge enclosed the surface, let us examine the case where the positive point charge q is outside the closed surface S. Since the flux phi E is given by the integral of the electric field E due to the charge q over the surface S, we can follow the procedure which we discussed in the case of the flux through closed surfaces in an inhomogeneous electric field. We split the surface S into the part S1 where the electric field lines are directed out of the closed surface, and the part S2 where the field lines are directed into the closed surface. Then we can also split the integral into 2 parts, that is the sum of the integrals of the electric field E over the surfaces S1 and S2. The first term is the electric flux through the surface S1 and the second one the flux through the surface S2, and these fluxes contribute to the net flux phi E through the closed surface S. We have also seen that the contribution of the field lines entering the volume enclosed by the surface S is the same as the one of the field lines exiting the volume. The only difference is that the first one is negative and the latter one is positive, that is the flux through the surface S1 is equal to minus the flux through the surface S2. As a result, the flux E through the closed surface S for the electric field E due to the point charge q outside the volume enclosed by the surface vanishes. Now we conclude that the electric flux through an arbitrary surface S enclosing a given volume for the electric field E due to a point charge q is determined by the integral of the electric field strength E over the surface, and it is equal q over epsilon naught, if the point charge is within the volume enclosed by the surface, and 0 otherwise, that is the point charge q is outside the closed surface. We note that we applied Coulomb's law for a single point charge to derive this relationship between electric flux and charge. The question is whether we can extend this result to multiple point charges, or even to a continuous distribution of charge. If we examine this question, we will see that such an extension of this result is possible, which is stated in Gauss's law. First we show how to extend the result to an electric field due to a system of point charges. Let us suppose that the point charges q1, q2, ellipsis, qn are within the volume enclosed by an arbitrary surface S. The total charge q in the volume is the algebraic sum of the charges qi in the system from I equals 1 to n. The principle of superposition for electric fields states that the net electric field strength E due to the system of the point charges is the vector sum of the electric field strengths EI due to the individual point charges QI from I equals 1 to n. By virtue of Coulomb's law, the electric field EI in a given point is equal to 1 over 4 pi times epsilon naught, times QI over the square of the distance Ri between the point charge QI at that point, times the distance vector Ri pointing from the point charge to that point, divided by its length. Since the electric flux phi E through the surface S is the integral of the net electric field E over the surface S, it is equal to the integral of the sum of the electric fields EI from I equals 1 to n over the surface S. If we exchange the integral and the summation, we can write that the flux is equal to the sum of the integrals of the individual electric fields EI over the surface S from I equals 1 to n. For the electric fields EI due to the individual point charges QI, we can use the result we have already obtained, and state that the integral of the electric field strength EI over the surface S is equal to the charge QI divided by epsilon naught for I equals 1 to n. If we substitute this equation into the sum, we will obtain Gauss's law, which is related to Gauss's theorem proved by Carl Friedrich Gauss, and states the following. The electric flux through an arbitrary closed surface S is equal to the sum of the charges enclosed by the surface, times 1 over epsilon naught, that is the total charge Q within the volume enclosed by the surface, times 1 over epsilon naught. If a point charge is outside the closed surface, then it has no contribution to the electric flux through the surface. In the next step, we will extend Gauss's law to electric fields due to continuous distributions of charge, where the distribution of a charge enclosed by a surface can be arbitrary. We can consider not only a system of point charges within a volume enclosed by a surface S, but also a charge distributed continuously along a curve calligraphic C with the linear charge density lambda, over a surface calligraphic S with the surface charge density sigma, or in a volume calligraphic V with the spatial charge density ρ, all enclosed by the surface S. In fact, the system of point charges and the charge distributed along a curve or over a surface are special cases of the charge distributed throughout a volume, where the spatial charge distribution is restricted to a set of points, along a curve, or over a surface. Therefore, we use the most general case with the spatial distribution of charge to extend Gauss's law to a continuous distribution of charge. Then Gauss's law for a charge distributed in a volume calligraphic V enclosed by the surface S can be written as follows. The integral of the electric field E due to the charge over the closed surface S is equal to 1 over epsilon naught, times the integral of the charge density ρ over the volume calligraphic V. By applying Gauss's theorem, we can transform the surface integral in the left-hand side of the equation to a volume integral. Then the integral of the divergence of the electric field strength E over the volume calligraphic V enclosed by the surface S is equal to 1 over epsilon naught, times the integral of the charge density ρ over the volume calligraphic V. Since the surface S, that is the volume calligraphic V enclosed by it, is arbitrary, the relation holds for any volume, and the integrands on both sides must be equal. As a result, we obtain Gauss's law in differential form, stating that the divergence of the electric field strength E is equal to the electric charge density ρ divided by epsilon naught. As opposed to the integral form of Gauss's law, the differential form describes a local relationship between the electric field and the spatial distribution of charge. The law states that the electrostatic field is a vector field, that is, describe the electric field strength E in each point of the space, which has sources. The sources of the electric field are charges, or more generally an arbitrary spatial distribution of charge, and the divergence of the electric field measures the intensity of the sources. Before presenting some applications of Gauss's law, we make a few remarks on the relationship between Gauss's law and Coulomb's law. Gauss's law and Coulomb's law are two different forms of the same fundamental law describing the interaction between electric charge and electrostatic field. This statement follows from the fact that Gauss's law is derived from the basic assumption that the interaction between electric charge and electric field is inversely proportional to the square of the distance between the charge and the source charge of the field. It is easy to see that Gauss's law does not hold for any interaction proportional to the distance to the power n, if n is not equal to -2. Let us derive the electric flux phi E through a sphere S with the point charge Q in its center for n equals to -3. Then the surface integral of the electric field strength E due to the charge over the sphere S is given by the magnitude E of the field strength over the sphere times the area S of the sphere. Since the area of the sphere is equal to 4 pi r squared and n is equal to -3, we have Q over 4 pi times epsilon naught times r cubed, times 4 pi times r squared, which gives 1 over epsilon naught, times the charge q over the distance r. As a consequence, the electric flux through the sphere S with a finite radius r for a point charge q in its center has a non-zero value. However, by increasing the radius r of the sphere and therefore its area S to infinity, we can diminish the electric flux through S to zero meanwhile the amount of charge remains the same in the sphere. This result contradicts Gauss's law. We also note that Coulomb's law can always be used to determine the electric field due to a given distribution of charge. However, with few exceptions, it is a complicated procedure. Gauss's law can primarily be applied for highly symmetric distributions of charge, which provides a very simple method to determine the electric field strength. In the integral form of Gauss's law describing the relationship between electric field and charge, the electric field E in the integrand is not necessary due to the charge q in the right-hand side enclosed by the surface S. Here we can see that the electric field and the flux through the surface S do not vanish. At the same time, the electric field strength due to the charge enclosed by the surface S is zero, and so does the electric flux through the surface, since the volume enclosed by the surface is free from charge. Therefore, the electric field E in Gauss's law can be due to charges both inside and outside the volume enclosed by the surface S.